All right, so at this point, we are ready to advance our understanding. Okay, and I still have not mentioned anything about polynomials, even though we started out tentatively to learn about polynomials, but I've been spending time so far talking about power functions. Okay, so let's look a little further into power functions. And so at this point, I'm going to creatively come up with a few power functions. Okay, so what I'm about to write up here is just a list of power functions that popped out from my mind creatively, on my own creativity. Okay, and you can create your own as well. So how about I'll pick a power 7. Okay, so x to the 7, and how about I'll stay with a coefficient. So we've learned all of these terms earlier, so now let's formally use it. So how about a minus 5, okay? Negative 5x to the 7, that's one of my the power function, okay? And then we can go with, how about, let me write it a little further to the left right here. So minus 5x to the 7, something that came out from my own creativity. And then what about I'll come up with another power function. Let's say x to the 4th power. Okay, and then here how about I'm gonna use a power 3, a coefficient 3. Okay, and then we can go with a power 2, so x squared with a coefficient 1/2. Okay, and then I can go with a power 1, just x right here, and now with a minus 3. Okay, so these are the coefficients corresponding to each of our power functions. So for now, all I need anyone who follows along with this video lesson is to see that this is just a list of power functions that came out from my own creativity. So I randomly popped out out of nowhere, okay, out of my own creativity with these 4 power functions. Okay, so now from those, this is what we can do. This is what we can do with these power functions right here. And keep in mind again, I used that term earlier. I introduced that term earlier that these are called a coefficient. But this is the coefficient for that power function, x to the 7. So minus 5x to the 7. Okay, so now this is what I can do. In the world of algebra, this is particularly the course content you're learning. So in the world of algebra, everything is an add, okay? Everything is an add. So now I'm going to purposely add all of these power functions together to come up with a bigger function, to come up with a more, the slightly more complicated and a larger function. And this is what I mean right here. Minus 5x to the 7. I can add with 3x to the 4th. Okay, somewhere here and there in some of your earlier or prerequisite course, you must have learned that we can add functions to create a new function. And so simply I can add these two I can add these 2 power functions. And now look at what I've had right here. I already created for myself a function. Okay, that's one way. Or I can add all of these 4s together. First, adding just these 2 power functions, I can already get some function. Okay, and now here, how about minus 5x to the 7. And really, the order of the addition does not matter. All due to creativity. First, I can come up with minus 5x to the 7 plus with a 1/2 x squared. And then, oops, I changed my mind. How about I'm going to additionally add in that minus 3x. We change our creativity all over in a lot of these works right here. Okay, and so that works too. We can come up with another function. Okay, so this one here particularly have 3 separate power functions that being added together, and you can see clearly that the minus 3x here came out as on its own as a power function. It was a minus 3x. But now, as I'm emphasizing right now, the concept I want to emphasize here is that we're going to add as a sum. We're going to add all of these power functions together. And what we have created here is a brand new function. What I created here was a brand new function that was a sum of these 2 power functions. What I've had here is the sum of these power functions. and they are already different functions. Okay, and then I can also create, I can also do, and by the way, so with this function here, yes, formally now adding a negative function, okay, gives me a minus 5x to the 7 plus 1/2 x squared, and you should be fluent with this algebraic skill at this point. Now we can legally write that as a minus 3x. All right. So this is our final function that came as a result of adding these three power functions. And again, these power functions came simply straight out from my own creativity, and you can come up with your own as well. Okay. And so now we slowly getting there, and I'm about to get into the point I'm trying to present here. Okay, so now we can even add all of these. Okay, and so I can have and I mentioned this earlier, but sadly I didn't mention a clear example. But so now here's the thing: you can also create something like this. First, initially we just plan to only add the x squared with the minus 3x. And then just like that, we change our mind. We want to add in something else additionally. So we can add the minus 5x to the 7. Okay. And now all of a sudden I change my mind again. I want to just completely add all these four. But see, my order currently is all over. Okay, there's no particular order. And now I'm gonna add with the remaining one in my list of creativity right here is that 3x to the 4th. And so here we have another function. It's different from that function. Different from that function. So these are all functions. I put them in a box just to indicate that these are all successful functions. It worked. They all, any of these works as a function. This is a function too. But then for something like this, we are going to purposely rearrange the terms, rewrite the terms. It's the way how algebra is, the way how the adding operation is. We can swap around the order of these terms, okay, and this is the first time I'm starting to use that. See, when you have an expression like this with and around the adding sign right here, there are multiple things here, and we call each one of these, it's a term, okay. And I believe you should have also learned that term right there from your previous course right here. So now I'm gonna purposely rearrange the terms in a certain order of these powers, okay. So this is a power 2, but it doesn't look like it's the highest power throughout the whole setting here of the four terms together. This is a power 1, okay. This is a power 7, and this is a power 4. So in that way, more conveniently, okay, or more systematically, I am going to rewrite all of those, even though what I wrote there can already legally be a function. Okay, I'm only saying a new function. I didn't mention any fancy new words at all. So I can just simply, it's our decision, and it's a good practice doing this. I'm gonna put the highest power first. So the minus x to the 7, minus 5x to the 7 comes first, and then the next highest one in these fours that I've added. Okay, the next highest one in these fours that I've added is this one right here. So I'm going to put that second, even though it's not, so even though power 4 is not necessarily the immediate consecutive power right down below 7. I'm not saying that these powers have to be consecutively right down below the other ones. Okay, but now at least I see among these four terms, among these four power functions, that I'm attempting to add them to create a new function. Then the 3x to the 4th, that power 4 is the next to the highest. All right, so now plus 3x to the 4th. And now anyone viewing the video is seeing where I'm going. So the next one here, needless that I have to swing back to the other board. So now it's going to be a plus 1/2 x squared. Okay, and then plus, and here plus minus 3x. So now this is just a purpose to keep things organized and being in a systematic, displayed way. All right, so we just once again, the whole story is nothing fancy. We just had 4 separate power functions, and I came up with this particular one by adding those power functions together into one large expression. And the extra step here, and as a good practice, we put these powers in a certain order, decreasing from the left to the right. That's one way. Some other time, some other mathematicians have their right to put these terms in increasing order from the left to the right. That works too. Okay, so for example, something like this, we can write it as, it's just optional understanding. Okay, we can write it as minus 3x, okay, plus the 1/2 x squared plus the 3x to the 4th and minus 5x to the 7th. That works too. Okay, so as long as we put ourselves in that good habit of arranging these terms, these power functions in a certain order of either increasing or decreasing order of the powers from the left to the right. Okay, so I don't need to keep this here on the board. I mean, you know, in the back of your mind that it's legal to do this. So now let's just focus, allow me to focus on the one I chose here. So this just means now we can write it as minus 5x to the 7 plus 3x to the 4th plus 1/2 x squared minus, okay, legally 3x, or formally speaking, so that's in the final simplified form. Okay, so let's put in some observations. So observations tell me that these are all, I mean, if we're looking at each one of these terms or each one of these individually as a power function, then we got this whole thing is a combination, is an adding, is a sum of multiple power functions. Multiple, pay attention to that word of mine. So we come up with something like this because we created a sum of multiple power functions. Okay, it's a sum, it's of multiple power functions. All right, so just like that, let's see if it's true. That observation is also true or was also true with the other functions that I created. See, starting with that one, I added two power functions together, multiple power functions together. Okay, and I had a sum. Same way with that one here, I added three power functions together to create this thing of mine right here. Okay, so I emphasize there are multiple power functions being involved as a sum. Multiple power functions being involved as a sum to create any of this thing. Okay, to create any of this thing. That's the first concept to come out. I mean, it's more detailed than that, but it's the first natural understanding so far. Okay, so ladies and gentlemen, multiple has a prefix. I call any of this. Okay, so this one here is a perfect example of what I so-call poly. Poly is a prefix for many or multiple. Okay, so this is a polynomial. All right. This is a polynomial right here. It's a polynomial. And so the same way, so now you're starting to click what a polynomial exactly is, because when it gets to this, allow me to approach this way so that you have a real hands-on and experience right through, some real hands-on experience right through the observation right here. So we call that thing a polynomial simply as I explained earlier. It's a sum of multiple power functions together. Okay, and I just now explained that term poly right here. It means many, multiple. Okay, and so this one here, yes, it's also it's another polynomial. So now I bring up that term, and now the one that we have here. So any of these is already a polynomial, but it's just not in a final form. Okay, so this is just to express originally how that polynomial came about, but formally or in a final expression, see, plus a negative, we're gonna write that. The better way of writing that is minus. But so this is a polynomial. All right, so think of where I'm going in this way right here. This is also tentatively I am creating a polynomial. Multiple power functions being added together. Okay, so that in my final form on the other board, yes, this is a polynomial. That one too. All right, so now for short right here, easiest to understand a polynomial. Welcome aboard to that world of polynomials. a polynomial simply is just a sum of individual power functions that come together. Okay, so that's the easiest ground to understand, the easiest core understanding to keep about a polynomial. But of course, there will be more details in that, and we will be investigating through, okay, throughout the lesson here. But at the most grounded level, a polynomial is simply a sum of power functions. Okay, power functions. See, this is a power function, and yes, I introduced that term earlier. So each one of these power of x, each one of these powers of x have a coefficient in front of that. And we will also get to any of those as well. All right, so here we go. We have a polynomial. We set up any of these, and they are all polynomials. Okay, so now let's look a little more into that before we generalize that into a formal definition. Okay, so there's a little more details than just simply a polynomial being a sum of power functions. Okay, so I tend to, in my style of giving the first time definition, I tend to mention the most attention-catching details about whatever thing I'm introducing. And then as you start getting that core, the most attention-catching understanding, and then I'm going to start adding in details that complete your understanding. Okay, so as a matter of fact, well, I didn't lie, and now I'm just going to add in additional understanding. So being a polynomial, it's not simply just a sum of power functions. Okay, here's why. Now, if you recall or even roll back to the earlier part of the lesson here when I was still introducing about power functions is a lot more than just these whole values of positive powers. As a matter of fact, we already had some exercise and an example that points out something like this. We can have a power function being an x to the 3/2 power. That works completely fine. Okay, I mean that was completely. I should have not said works completely fine. But what I meant is this is completely legal as a power function. It's a power function. I mean it came out from x square root of x. Okay, it's a power function. Okay, but then something like this, x to the 3/2 plus x to the -2 power. See, it's a power function. But something like this is not a polynomial. Something like this, unfortunately, not a polynomial. So wait a minute, is the professor here lying? No, because I did not tell all of the details yet. Because if we simply just stay at a polynomial is a sum of power functions, then with such simple rule, then there are going to be way too many polynomials existing out there. And so now we're going to start limit down the criteria, okay, to know what really qualifies to be a polynomial. So there are more than just being a sum. So there are more details than just being a sum of power functions. Okay, so yes, the most attention-catching understanding is that a polynomial truly is a sum of power functions. But this is a sum of power functions too. But it didn't work out. It was not, at least the professor here is not considering this as a polynomial. So why is that? Because these powers, we want to specifically focus on those powers being 0 power or more and whole value. Okay, so now I'm going to say, make a note of this. Okay, each power must be non-negative, meaning greater than or equal to 0. See, non-negative. I'm talking about each of the powers right there. So each power must be non-negative and being an integer, or that should be the most precise term like that. So each power must be non-negative, okay, and be an integer. These are the two requirements. The two other details, not any less important. Okay, so as I said, all I'm saying is any time I give out a definition of what it is, I tend to talk about the one that's most attention catching. So being a polynomial, what mostly catches people's attention is that it's a sum of the power functions. And once we got it nailed down, there are more details in that being as important as it can be. Okay, each one of these powers have to be, see, this is power 1, non-negative, that's power 2, non-negative, that's power 4, non-negative, and any of these powers is an integer. All right, so that's what makes a polynomial. Okay, so a polynomial is, yes, the first thing to understand, it's a, see, poly means, see, that's why it's most attention catcher, right in that term right there. Poly means many or multiple. So many of what, or multiple of what? Multiple power functions that come together. But each of those powers has to be non-negative and being an integer. Okay? And so now there's even more details, but not as important because it's always there. And each one of these polynomials, each one of these power functions has a coefficient. Okay, each one of these terms term that came originally as a power function has on its own a coefficient. Okay, so each power function, okay, has a coefficient, and that's there are even times where I'm teaching a face-to-face class and I even forget to mention this last statement right here, and my students are just gonna click through that just fine, because even if I forget to mention this last detail right here, of course it's the way it is. Any value, even if we don't see anything, even if I simply go with x to the 7, oops, no number, it means there's a coefficient 1 plus x to the 4th plus x squared. See, if you're looking at completely without these coefficients, that's not really without these coefficients. These are coefficients 1 times x to the 7. So coefficient is just a constant value that being multiplied in front of each of your power functions here. Okay, and so that's why, as I said earlier, having this statement that I just wrote down right here, having that in your mind or not, it's not really too important because it's always there. Those coefficients are always there. Okay, so admittedly, throughout times when, as I said earlier, throughout times when I was teaching a face-to-face class, or anytime I'm teaching a face-to-face class, there were times I forgot to mention about this last detail, but it did not impact the understanding of my the pre-calculus students, simply because it's the way it is. It's always there, needless for me to mention. Okay, so now this is all the details we have about a polynomial. Okay, and as a matter of fact, there's going to be, so I am going to now write down the formal definition. Okay, but before we get to that, let me just stick right here on this lengthy one. Okay, even though we've got more examples of a polynomial than that, but let me just stick with this lengthy one, and then to explain some more details, some more understanding, and then I'm going to get back to this board and then write down the formal definition. Okay. All right, so now with that one, I said I would like to retain on the board here, so minus 5x to the 7 plus 3x to the 4th. So how about allow me to do this. As I'm writing it down before I'm able to give any explanation, someone may feel a little shocked with what I'm doing. So from minus 5x to the 7, I'm going to leave a gigantic space right here and then add 3x to the 4th. Okay. And then add, okay, and then here about 1/2 x squared, okay, and all of a sudden, you notice I purposely left some gigantic space. It's not that I'm wasting board space here. There's a reason why I'm doing that, okay, minus 3x, And by the way, that was an x squared. Okay, so this is my intention. This is just another truth that comes out. I mean, believe me, there are students who, without me pointing this out, you will naturally be able to tell. Okay, so I'm only saying that just to make you understand that this is just understanding that's naturally easy enough to pull it out. But just because I'm pointing it out right here doesn't mean anyone taking this is not understanding it. Okay, so it really doesn't mean to offend anyone or anything like that. That I have to talk about some silly stuff. So from the x to the 7 to the x to the 4th like this, I just want to explain a little more about the nature of these coefficients. You see, we don't see it. I don't see it here. I'm talking about seeing what? I'm talking about the x to the 6th and the x to the 5th. We really don't see that here. And in my list, that didn't even happen. I didn't even creatively come up with anything with x to the 6th or x to the 5th. Okay? So now, that gigantic space of mine right here, I just want to emphasize the fact that really there's another truth behind the scene here. You see, there's such a big gap between x to the 7 and x to the 4th. Okay, for those who already recognize, that's good for you, but for those who are not experienced, here's that experience I'm putting into your understanding. That's why, like I said, just as you learn through this, don't feel offensive or anything like that. If I have to mention some of the details that seem to be a little too basic, but it will be good for you to build that foundation right here. You see, it really means we can add with a 0 x to the 5th, x to the 6. Okay, and then add with a 0 x to the 5th. So now I purposely had a polynomial where it goes consecutively in those powers. It's still true that in this real polynomial I had, here, those were all the terms we saw by our own eyes. Okay, but the real truth behind the scene, is that there are behind the scene or hidden terms, that being 0x to the 6th plus 0x to the 5th. And then I brought this up. I brought these out to light, hopefully to make you aware that we can now purposely put our polynomials in a way that it's going consecutively down with these powers. So it started out with power 7, and it went, we didn't see power 6, give that a coefficient 0, so 0x to the 6. We didn't see a power 5, that means the x to the 5th is there, but with coefficient 0. All right, and then x to the 4th, okay, with coefficient 3. So now you're seeing where I'm going with that empty gigantic space here. It means we're looking at add 0x cubed and add with x squared and minus 3x. All right. The reason I'm doing this, the reason I'm pointing this out, because I'm slowly leading you into that formal definition of a polynomial. Okay, so a polynomial in practical situation, we don't have to write down all of the powers from whatever it starts down to wherever it ends. It can be just the formal final one like this. Okay, and where you simply just need to keep that as it's simply a sum of multiple power functions that added together. Okay, and then each power has to be non-negative and being an integer. That's really all you need as the core understanding. But now, as I keep making it more to light, those other hidden details that now being brought out to light right there. Okay, so, and the reason I'm doing that is once again because we're slowly getting into that formal definition of what a polynomial is. Now, my challenge for teaching this class is that specifically about polynomials is that, again, like I introduced earlier, before the lesson started, then there are PhDs who spend their entire life to study about these polynomials. And that's the reason why what I mentioned there is to indicate that we have a lot of details. We have a massive amount of details regarding these. And so the challenge for for any of us, the pre-calculus instructor, to give out the details that we're still trying to look for that balance point between what's deep enough for a pre-calculus level students like that versus the kind of details for the real pro, the real experts out there. Okay, and so it's easy to keep understanding about the polynomial as a sum of power functions just fine, like how I wrote that. But when it gets to the formal definition later on, allow me to stick with the formal definition that generations of mathematicians have been using it. Okay, and that's the reason why I'm slowly going through all of this. Okay, so one more hidden detail here. So we go, well, we started out with that highest power, admittedly. Okay, and then the 0 to the 6th, 0 to the 5th, 3x to the 4th, plus 0x cubed, so on and so on. So we landed down to x to the first power right here. There's one more term. There's one more. Really, formally speaking, any polynomial will have a constant term. So I'm going to, here, we don't see it. We don't see that constant. It's not like a plus 5. It's not like a minus 3 or anything like that. Plus is 0. That we call it a constant term, and I will formalize all of that. All right, so now we are ready. So here in this way, I'm observing this. This is what I see right here. I call this a polynomial, okay, and it goes from, well, the highest power it started is a 7, and it goes sequentially or consecutively down on the powers with the coefficients switching between positive, negative, or even zeros. And then it goes all the way, keep reducing the powers consecutively down to a constant term. All right, and so now I'm going to turn to the other board and start writing down the formal definition of a polynomial. All right, so definition. Okay, so a function, okay, a function or any function in the form, all right, or any function in a form, okay, f of x equals, so some x to the n start as the highest power we recognize, some x to the n as the start as the highest power we recognized. Okay, so again, let me hop back to the other board a little bit. See, so at least in the one I created here from my own creativity, and you can make your own polynomial as well, there will always be a highest degree, a highest term, the highest power that starts. Okay, and I accidentally used that term a little too early. We'll get to that formally. So it started out with a highest power. Okay, and then so here it's power 7, and then we can write that as power 6, power 5, and so on, and keep sequentially losing down the power, decreasing down the power like that. Okay, and then these are the coefficients, and so now generally speaking, I can see that this is x to the 7. So as a general setting, as a general understanding, I see this is a coefficient. It can be positive, it can be negative, but I call that as an a to the 7. How's that? A sub 7, it's a coefficient attached with our power n particularly. Okay, so here is power 7, I call it a sub 7. This is x to the 6, okay, that 0 right there is a coefficient a6. The value is a 0, but generally as a setup, it's a coefficient a to the 6, corresponding to that 6th power. And then we're connected them by added. See, so it's power function, another power function to the 6, another power function, and so on and so on. Okay, and keep leading it down to, so this one here is x to the first power, so 3 here is called a1. All right, so this 3 here is called a1. So that 1/2 here, it's corresponding to the x squared term. We can call that it's an a2. That's what the 1/2 is for generally. Okay, and so now I'm even more ready to tackle down that formal definition. So any function in the form of some power n starting, okay, with some coefficient that I call that, namely an. And I'm going to add, see, it's a sum of power functions. And then we purposely write them in a certain order. So here I go with decreasing order. So now the next term has to be, the next power function has to be 1 power lower. So n minus 1. Makes sense naturally that way. And then a n minus 1. Okay? And then the next one down is x to the n minus 2. 2 power down, 2 power levels down, 2 power steps down compared to the first started one. So the coefficient here is a n minus 2. Okay, so corresponding to x to the n minus 2. All right, and keep adding until we run to the, see, this is a 2x squared plus a 1x. This is power 1 and plus. So now we see eventually think about, after we squeezed out all the powers here, then this last one here is a constant term, so I call it a sub 0. This is a constant term. All right, so any function in this general form right here, in this form, okay, is called a so now here's the formal term right there. It's called a polynomial. All right. It's called a polynomial. And now there's even more. In this one definition, allow me to introduce some more terminologies here. So this whole setup here is called a polynomial. But now, to be more precisely, it's a polynomial of degree. Okay. So how about I'm going to write that in red ink again to make it a formal term that's worth your attention, of degree n. Okay, it's a polynomial of degree n. Okay, put a comma here. Provided or given that, you see, so, and I will get more into explaining what degree means. But you see, degree n here just means the highest power that we recognize ever in our polynomial. So, and I'll get more detail into that, but the coefficient that stays with that degree right there, okay, has to be a non-zero. It can be negative, it can be positive, but just strictly non-zero. So provided a sub n, okay, the coefficient with the highest power, and you can see that I call this degree n, where I'm writing this general setting with the highest power to be the n power. So this polynomial is called polynomial of degree n. Okay, but then in order to call it degree n, we have to make sure that the coefficient, it's the way it is. The coefficient with the n power here has to be a non-zero coefficient. Okay, and so now, and any of these other ones, all of these are values, a to the n minus, a sub n minus 1, a sub n minus 2, okay, all the way down to a1 and a0. That list of all of these coefficients can be any real numbers. All right, that's the requirements about a polynomial of degree n here. We need that coefficient that stays with that highest power to be non-zero, and then any other coefficient, and these are all coefficients of that, and we will also mention that even more clearly. Okay, but in a formal definition, this is what it is about a polynomial, and specifically a polynomial at degree n right here. Okay, so now let's make a couple of remarks right here, and I'm gonna look at this thing side by side with that current example we're having, so that you will have it more clear about what's being written in this definition right here. Okay, and of course, at any instance here that if you need to, feel free to pause the video to take notes on this formal definition. And admittedly, I am using a definition that came out from a book I chose, but it does look a little lengthy for somebody. Okay, but I believe this way is making it clear and with enough details again, but not to not too overwhelming. Okay, and so now I'm going to keep switching back and forth between the two boards here. So now in my formal definition, I brought in that term degree n. So now admittedly, when I break this down into a form that's matching with how I gave that in the definition, and I made it come out to light earlier that, see, we are also supposed to have a constant term right there at 0 in this particular minus 5x 7 plus 3x to the fourth plus 1/2 x. I mean, surprisingly, it was a short polynomial, only 4 terms. But then we now understand in the back of our mind that there are all these terms right here going consecutively down. That's why I was explaining. See, these are meant to be after the highest power recognized right here. All of these powers going sequentially or consecutively reduced until all the way down to power 1 and then no power. Okay, constant term. All right, and so really the one polynomial is sometimes have only 4 terms, but after you're looking at your highest power, then all of those other terms are all there. Okay, and so that's why, like I said, any of these coefficients can be just any real numbers, including zeros. And that's why now in this in that way how I wrote down the definition, see, these are coefficients being non-zero, okay, but then there are coefficients being 0 too. And this very first one, all right, this A7 in our case right here, or specifically as a value minus 5 right here, okay, that one here has to be non-zero because it determines the highest. This one here has to be there because it determines the highest power in our entire polynomial. So now here, observation is telling me that highest power, okay? See, that's why it's important to have the coefficient with the highest power to be non-zero. Otherwise, if it's also a 0 here, then we can completely disregard all of these guys and consider x to the 4th as the highest power. So now highest power here is, in this case, 7. That's the observation. And that's the reason we have that existing here, because of that coefficient being non-zero. You see, right after that, there are already 2 0 terms here. So if that one was also 0, then the whole 3 terms here disappear or vanish. And it's going to start out as that 3 to the 4th as the highest power in your remaining polynomial. That's why in that way, you know, in order to decide the highest power in your polynomial, you have to, or this is for anyone who are about to write your own polynomial. Okay, then if you want to say your polynomial has 7 being the highest degree, being the highest power. Okay, I'm keeping ahead of myself a little bit. But if you want to claim that if you want to write a function where the highest power being a 7, then the coefficient with that x to the 7 has to be non-zero, and then anywhere else above that is all 0 out. That's why we just started with that power 7 and going down. Okay, now the observation here in this polynomial I gave out as an example, highest power is 7. All right, and then in that way, so now let's get clear with that term I use on the other board, the degree. So that means in this way, okay, this is a polynomial of degree 7. This polynomial over here. All right, so now we have a clear understanding of what a degree means, okay? So the degree, okay, is the highest power, okay, in the polynomial. All right, that's another understanding to mark down like that. The degree is the highest power in any polynomial we're looking at. So if right now we're working with this polynomial right here. The highest power we recognize, the one that comes with a coefficient being non-zero. Okay, that determines the degree. So this particular one I'm working with, that's called, this is a polynomial of degree 7. All right, so now allow me to, I'm still going to retain this polynomial here. But now I'm going to quickly write down, and sadly, I just wrote this down not too long ago, but just allow me to erase that out, because I still want to retain the definition and retain this little example. So earlier I introduced minus 5x to the 7 plus 3x to the 4th. It's not the same as this one. It's shorter, okay? Because again, think about this. This is the same as minus 5x to the 7 plus 0x to the 6 plus 0x to the 5th, okay? Plus 3x to the 4th. And then we don't see anything else after that. It means all 0 out. So plus 0x cubed plus 0x squared plus 0x plus 0 for constant term. But surprisingly, it's only a polynomial of 2 terms short. Okay, but now I can formally say this polynomial is degree. See, even though I purposely wrote it in a quite lengthy format right here, in a quite lengthy form right here, but in the end, the highest power recognized, the one that comes with a non-zero coefficient here, degree 7. That's the one. So throughout my creative work earlier, we already looked at 2 7th degree polynomials. Okay, so the polynomial has degree 7, but another way of saying, you know, this is a 7th degree polynomial, and this is also another 7th degree polynomial. They are not the same function, you see, because this one here, after x to the 4th, we still have some other non-zero coefficients, square power and first power, okay, whereas here after the 4th power everything was 0. Okay, so the coefficients also decide the polynomial being a different polynomial, even though they may have an equal degree. All right, so those are more the details I keep putting in, and that's why, like I said, so only the coefficient that decides the degree of your polynomial must be non-zero. Any other coefficients of those corresponding but lower powers, they can be 0. They can be any real values. And that's why, once again, it emphasizes our understanding here. Okay? Any of those coefficients starting from the one immediately less than your starting highest power right there, any of those coefficients can be just any real numbers, including 0. All right, so now that's the definition. But then there are still more details, more fascinating details, and this is so far we're just getting to know, and we're just getting to be comfortable with the way how we call these names like that. Okay, all right, so now I am getting back to this board right here. So this one here, even though 2 terms, I made it clear earlier that it really has other terms like that, but those coefficients there are all 0. Okay, but at least this one here we know it's degree 7. All right, so now, yes, so here needless to say each one of these coefficients, now we formally call them, these are the coefficients, just like coefficients of power function. Now these are coefficients of your polynomial. They were coefficients of your power functions, and now when we put those power functions together, okay, they become these numbers right here. They become the coefficients of your polynomial. So now I can formally start using that term, the coefficients. Okay, these coefficients right here. Okay, the coefficients of the polynomial, or for short, the poly. Okay, of the polynomial. So these are coefficients. But now even more specific. See, that one here I wrote that, I underlined that with red ink. That one here I underlined that with red ink. This specific one, that specific coefficient that stays with the degree, that stays with the highest power we refer to them as the leading coefficient. The leading coefficient. Okay, just that number. All right, the leading coefficient. And so in that way, so now each one of our power functions, because remember, a polynomial is a sum. It's a sum of the sum of power functions, of multiple power functions. So now when we put many power functions together in a sum, okay, then each one of those now naturally, we've learned this term in our previous course, and now we use those terms again. Each one of these power functions now, it's a term. It's a terminology, and now we also call it's a term. So this is a term, this is a term, okay? So now I just now realize that my board is getting a little too tight, too squeezy. So now we understand what coefficient is and what a leading coefficient is. So now we're gonna call each one of these, see, any of these is in the whole, each one of these power functions that came as part of our overall polynomial. These are the terms, okay? So that whole thing here is a term. These are all terms. Okay, first term, next term, and so on and so on, and even this last one right here is called the constant term. All right, that's the constant term right there. Any polynomial has a constant term. Okay, it can be any real value. It can be a positive value. It can be a negative value. It can be a zero, like in this case. But so any polynomial has a constant term. All right, and so now I was talking about leading coefficient. So a coefficient is just that constant value multiplied in front of each of your term. Okay, that, like the A6 right here is a coefficient. It could be 0, it could be the negative, it could be positive, as long as it's, as long as it's with the term being below the highest power. So the coefficient for the highest power, we call it the leading coefficient, and it always has to be the non-zero. Okay, so leading coefficient. But now, and again, I have to quickly erase this. So the term that has the highest power, we call it as a leading term. So minus 5x to the 7 plus 3x to the 4th plus 1/2 x squared minus 3x. This particular polynomial, see, the leading coefficient is negative 5. And this first term right here decides the highest power, which eventually decided for us. This polynomial is degree 7. So this entire term being circled here, we call that, this is the leading term. All right, that's the leading term. Okay, so now we have had enough the vocabs. Okay, so far it's just the vocabs so that we get to know and how to communicate properly between instructors and students in terms of these talking about these polynomials. And outside of my class, outside of the group of students who study with me, right? When you go on and communicate with any of your other professors for math help or anything like that, they will use these standard terms like that. Okay, so there are leading coefficients, there are leading terms. Okay, there is a degree. All right, and then there are the coefficients, there are the terms. Okay, so now at this point, let's look at the following. And so just like what I said earlier, and then shortly I'm going to need to go back and make a remark, sort of like an additional detail right there, but quite important in my definition of the polynomial. So I brought this up earlier. So now something like this, minus 5x to the 7 plus 3x to the 4th is a polynomial. Okay, but I also brought up earlier that how about an x to the 3/2 power plus and x to the minus 2 power, something like this. See, we got coefficients too, and we got coefficients, okay? But this thing here is not a polynomial. All right, it's not a polynomial. So why is that? Because when we're working with polynomials, we don't want these kinds of power. We don't want those powers. We want powers to be just, whole values, integers, or integers and non-negative. Okay, and so now we're gonna add a remark here, like that. Okay. As a remark. Okay. And when we write it into a remark, we only need one value, and must be or an integer, or how about a non-negative integer. All right, and must be a non-negative integer. Okay, so how come I don't mention about all the other ones? Because once n is given, an n here in the way how I'm writing this general form right there, then this n right here is, as long as we know that it's the degree, it's the highest power, and it's once we know that it's already a non-negative integer, then any of these guys right here, okay, it's gonna go sequentially down. So being a whole number, subtract 1 from a whole number is another whole number. Subtract 2 from the whole number is another whole number. Okay, so we strictly need that leading power that decides your degree of the polynomial to be non-negative integer, and then of course consequently any of the following powers must be non-negative integers as well. Okay. And then of course we're gonna stop whenever it hits down to power 1, okay, and then end with a constant term. And that's why all we need to do, again, we only need to have n being the degree of your polynomial, just simply need to be a non-negative integer, okay, and then any of the following powers will be non-negative, because they're just simply subtracting 1 or subtracting 2 or subtracting 3 and so on sequentially down from our starting degree right here. All right, so that's how it works right here. So now, in that way, I am going to do a quick little activity right here to really shock your attention a little bit, okay? So that you will understand. I mean, it's to broaden your understanding, and it also I also want to emphasize how important this class of functions that we're learning right here, the polynomials. And so at this point, a polynomial is not simply just a function you are seeing that matches with this definition. Okay? We have seen long ago, from quite a few courses before this, our what's so-called the linear functions. Okay, linear functions. It was already itself a class of function where it's in the form of an mx plus b. Linear function. Slope, intercept. There were so many ways of calling it. Up until this day, when you're learning at this level, we're still calling that slope intercept. Anytime we would like to see that as a linear function. But now, hey, if we're looking at this a little more closely, if we're looking at this as a sum of power functions, isn't that a power function? This is power 1. Leading coefficients, m. Okay, and this is a constant term. So, yes, ladies and gentlemen, pause the video and think about what I just said right there. But now I'm telling you another truth. A linear function is a degree 1 or first degree polynomial. All right. And I'm sure you have learned about linear function. We've spent almost an entire course in elementary algebra to learn about how to operate fluently with linear functions. All that slope-intercept form and all that. But in the end, now we realize all of a sudden, once we've learned about what a polynomial is, we now just realize that function we've been working with throughout all of those times prior to this course was a polynomial. We already learned about, so we already started getting to know about that polynomial. So now linear function is a degree 1 polynomial. Nail that down for clear. Okay, and that's why I said a little. This information I'm telling now may shock somebody in a sense that it's now all of a sudden it enlightens your understanding. It's broadened out your understanding. Okay, there's more. So in the way how algebra evolves, in the way how we learn algebra, okay, after linear function, then we moved on. We went on to the following, and I'm sure you're familiar with that still at this point. The f of x equals the famous ax squared plus the bx plus c. Yes, ladies and gentlemen, this is our famous quadratic function in standard form right now. Okay, and it's that name, quadratic. Okay, quadratic function, ax squared plus bx plus c. And then your instructor back then, in your prerequisite course, when I say back then, I meant in your prerequisite course, your instructor back then should have mentioned that, see, in order to be considered as a quadratic, that a, right, the coefficient that stays with your square term, with your quadratic term, has to be a non-zero term right there. Has to be a non-zero coefficient. All right, but now why am I mentioning about this? Because now if I see this is a sequence of powers going down from power 2 is the highest, and then power 1, then a constant term. So now what do we realize? In connection with what we're currently learning about a polynomial. This is power 2. We can recognize that a, it's a coefficient. So how about a2 plus this b right here goes with the power 1 term. So I can see that as a1 corresponding to power 1. And this is a0 for the constant terms of that quadratic. So all of a sudden we realize, yes, a quadratic function we used to know. We used to spend so much time learning about that. And the graph is a nice parabola and whatsoever. But in the end, this is one member. So linear function was a member. And then the quadratic was also another member. Is a second degree or degree 2. Degree 2 polynomial. No doubt about it. Now it's brought out to light. Okay, that quadratic. Okay, and so now I'm running short of space right here. So allow me to erase the information we've written here, and then I'm gonna add in some more. So we've had linear, we've looked at quadratics. Shockingly, they're all members of our polynomial. All right. And so now in that way, we have seen somewhere here and there a cubic function. Like among your toolkit functions, that's cubic right there. Okay, simple cubic or just for now a cubic. Okay, and then in a more general form, some ax cubed plus bx squared plus cx plus d, 4 terms things. Okay. But first term here, the leading coefficient has to be non-zero. Any of these guys can be 0. That one can, the b value can be 0, c value can be 0. The constant term can also be 0. But except for that a term, that a coefficient associated with that x cubed right there has to be non-zero. So, okay, a is non-zero. But see, this is a general cubic. Some of your instructors in the past course might have emphasized this, but some other instructors don't. But you must have seen this once or twice in your prerequisite course. Okay, this is a simple cubic, but this is a general cubic right here. Okay, so now this is how I see that. Well, x cubed. So that area here, why don't we think of that as some coefficient, some non-zero coefficient that goes with the third power, so I call it a3. That here, I call that a2, okay? And yes, adding between those two. And then that c right here is an a1 that goes with first power, and that last term right here is a sub 0. This is another polynomial, okay, of degree 3, a cube, 3 dimensions, okay? This is third degree polynomial or degree 3 polynomial. So now that, again, further enhance our understanding, is a degree 3 polynomial. All right, so we keep getting ourselves better and better at recognizing polynomials. Such a powerful family of functions. It covers all certain now. Once we are introduced to the word of polynomial functions, then we realize a lot and almost all of our functions we have seen prior to this course right here are all polynomials of lower degrees right there. Okay. All right, and so now at this point right here, once we have realized how broad, how big this family of polynomials have, okay, how big this family of polynomials has as far as the number, the amount of the members being involved in that. So we start putting into our question the following curiosity question. What about those power functions we have seen earlier? What about those power functions we have learned right before we started getting into the polynomials? Say simply just a sum like this. Okay, just that negative 5x to the 7 itself right here. All right, so now if we're sitting back a little bit and think through a little further, this one's a power function with a coefficient negative 5 with an x raised to the power 7. But now just this only term standing by itself, yes, this is also a polynomial. Okay, so once we have understood about polynomials and having coefficients and those coefficients after, assumingly after this is the degree, this is the term, and the only term that determines the power, the degree of your polynomial, then everything else, any other term after that, in the way how this looks right here, any other terms after that has 0 coefficient. So we can think of this one here as plus 0 x to the 6 plus 0 x to the 5th plus, and all the way down to, and even the constant term is a 0. That's completely legal. That is completely legal. And so now my point is, even something this short, only one term that we're seeing right in front of our eyes, or just in another name, just that ordinary power function with a coefficient, that itself deserves its place to be a family in that polynomial functions. So this is a polynomial just fine. Okay, this is a polynomial just fine. If you are seeing this as adding with a whole bunch of other terms like that, but all 0 coefficients, that's one way how you're seeing it. Okay, and then so it's just me that when I teach, I really love to deliver as much details as I can, in case there are people who really love studying about this. And so a very short polynomial this way, or another way of saying a polynomial but simply just one single term like this, this term has been forgotten for a little while, but formally a one-term polynomial in this way I'm describing, yes, it's a polynomial, but specifically, so now I'm talking about as a detailed name here, specifically a one-term polynomial aside from being regarded as a power function. This is also referred as a monomial. Okay, this is just for anyone who would like to know. Okay, but this term right here, as I said, in these recent years right here, it's starting to get forgotten. Okay, only maybe if you speak to a professor who is in the older generation of mathematicians, then they use this term quite often. But in the later generations, then we haven't heard this term as much. Okay, so see, mono means just one. All right, so anytime that we're looking at or just any of those single term polynomial, yes, we call them as a monomial. Okay, or just by itself, yes, it's a power function with a coefficient. All right, and so now we even realize how big that family of polynomial is. Okay, so I even want to mention the following detail. So what about the constant term itself? The constant term itself. And when it gets to this, I have to promise to myself to keep it as a certain limit, because it's still, even just about this particular topic, it will get lengthy into lots of details. And I want to save those details for any of you who plan to take some more advanced course in mathematical analysis. But here, at this beginning level of algebra here, we are in the pre-calculus level. So allow me to explain about constants. Okay, constant term or a constant function. The constant term, but more generally, I would like to discuss that as a constant function. So let's say we have a function f of x be just some constant. So anyone at this point learning about a polynomial, you must have gone through learning about what a function is. So a constant function, the idea of a constant function is that regardless of the values for the x input, doesn't matter what input x values we give the function output's value remains c, remains at constants once it's given and defined. All right, so for example, f of x equals 5, that's one constant function. F of x equals 10, f of x equals negative 5. So once we have a constant function defined regardless of the input value, okay, our function's output remains always that constant. So that's why it's called constant, because the output constantly stays on that value. But now, why am I bringing this into our discussion about polynomial? Because as we have realized earlier, pretty much any function, any polynomial function ends up with a constant term. But wait a minute, we don't see power. That's the whole point I want to start leading your attention into. It's in a way how that definition was. So I made viewers and students of mine to fall into that impression that a polynomial is a sequential sum of those powers that's consecutively dropping down. But why is it all of a sudden after power 1 it's no more power? What exactly is the idea here? The truth now is that there is still power. There is still power in your constant term, in your or constant function itself. Here's how I want to trigger your understanding. But then right after this point right here, then I want to take a sort of like a stop on this particular detail, because it has an entire limitless journey out there to investigate carefully about constant function, to think of that as a power function. Okay, so here's how I see it. Needless to say, any constant c is a c times 1. Any constant c is a c times 1. It's just the way how our algebraic understanding is. Okay? And then with that 1 right here in our algebraic understanding, we see 1 here as, think of that as, if x is the input, think of that as x raised to the power 0 over here. Okay? And so yes, constant function can be regarded as a power 0, and that's why it fits, it makes its perfect seats in the whole family of a polynomial. So now legally speaking, so this is a 1 power term right here. This is a 1 power function. And then you can also see that as a monomial, or you can see this as this is the constant term, right? Or the last term of your polynomial. So now in other words, this well deserves its place to be, this is a polynomial. Okay, it's a polynomial as well, or it's just the last term, the very ending term of your larger polynomial. Okay, but again, as I said, there are still a lot of mysteries about this, especially it gets dangerous for those who go into higher course about expressing 1 as an x to the 0. So that's why allow me to stop the details here. I mean, I'm not saying that there are no more details, but those other and more advanced details, if you recognize that, questioning me in this class is not a good place. You can wait until like a course in higher course in either somewhere a little bit past calculus 1, or maybe your calculus 1, or even some higher course in mathematical advanced mathematical analysis. That's where we can pull out all the real clear details. Okay, but right now, if you recognize any mystery about this, in a way I'm explaining right now, then questioning me that at this point right here is not a good place yet. Okay, I'm not saying that I won't be able to have an answer for you, but that answer also needs you to have a proper experience enough, okay, a strong enough experience to pull through all of that details. So here we only need to take that on the simple side, that yes, even a constant function can be legally regarded as a power function, and consequently now it's a polynomial. Okay, simply because c means it's a c times 1, and 1 here we can think of that as an x to the 0 power like that. All right, so now I keep pointing out more and more functions being involved in that family of what we so call the polynomials. All right, so now in this way over here, along with what I just introduced, and this x of 0, see, there's a reason why it's called the x of 0, because think about each of these coefficients as being corresponding to its current power position. Then see, A2, coefficient A2 is corresponding to the power 2 position. Coefficient A1 is corresponding to the linear coefficient, the linear power 1. Then that means this is, see, A sub 0. Whoever came up with this way of indicating a polynomial already had some intention. Okay, and so this A sub 0, needless to say, we can think further that yes, it is, even though not written out specifically, but it is corresponding to the x to the 0 power right there. All right, so, but again, that should be just enough details with that the constant term being expressed, being well qualified as a member in our polynomial. Okay, so now we're still going to have more details about polynomials, okay, before we are able to head into certain examples. But now let me show you a different way of looking at a polynomial, All right, so now so allow me to bring up the following very simple example. It's not a formal example, it's just something I'm bringing up as a demonstration. And I'm bringing back some old ideas that you have seen from your previous or past courses, okay? And then from there, we're going to realize another way of looking at a polynomial. Okay, so I'm pretty sure you have seen, let's say, a quadratic like this, x squared minus 4x plus 3. All right, so this function, yes, in our old term, it's a quadratic. And just now, alongside with this discussion right here, we got through that it's regarded now, it's also formally understood as a polynomial, a degree 2 polynomial. Okay, so that should now be enough with classifying this kind of function. Okay, but my point I would like to bring up here, or what I would like to bring up here, is that you must have seen the following work. Factoring, okay? No doubt about this. Anyone going through that prerequisite course about algebra right before calculus, you must have gone through at least a few times factoring work, where you factor a quadratic like this into 2 factors. So bring in as much of experience from your past courses as possible. Okay, so a polynomial like this can be factored into an x minus 3 and an x minus 1. Okay, I'm not trying to give a lesson on how to factor, but we know at this point in our experience, in our learning experience through algebra, that this quadratic here has an equivalent factor form. This is called a factor form. Okay, this is a factor form, or the factor product. Okay, and so if we apply the foiling work, the idea now is that if we apply the foiling work, see, x times x gives us the x squared term, x times -1, and then x times -3 times x right here. These two will combine like term and give us that middle term being -4. So this is just, so I'm just trying to point out that these two are exactly the same polynomials. Okay, but so what is the bigger generalization I'm trying to bring up here? Okay, so polynomial you have seen with the definition I had on the other board. Polynomial we're seeing this way, where we list down every term, where we arrange the terms from high power and keep reducing down to this form right here. Okay, is regarded as the general form. All right, and so that's why allow me to use a quadratic to keep things small and simple but representative enough. So this is now, if you're seeing this as a polynomial, see, it's being arranged in, well, right now I'm using a decreasing order in the powers. Power 2, power 1, constant term, or namely power 0. Okay, this is called the general form. Yes, a polynomial written where we list down all the terms with coefficients, with leading coefficient and all that. Okay, and then in a certain order of powers. That's, allow me to repeat that part. And so this is called the general form. All right. Versus now, I'm bringing up that example particularly for a quadratic, okay, a second degree or a degree 2 polynomial. And I pointed out that this polynomial outside of the general form, it had a factor form. Okay, it had a factor form. And so that generalization I would like to bring up for any polynomial, okay, a good amount of times, a high percentage of times, it comes with a factor form as well. Okay, so make a good note on that. So this a to the n x to the n, a n x to the n plus a n minus 1 x to the n minus 1 plus etc. down to a2 x squared plus a1x plus a sub 0. This form right here is called the general form. Okay? Just like how I was making that name right here for a degree 2 polynomial. This was the general form where we list down all the terms with the coefficients. General form. Okay? But now another way of saying a lot of times, and I only say a lot of times. Okay? But now we can make a note of this. Or a little more precisely, many times, okay, a polynomial can be given, okay, in factor form. All right, in factor form. All right, many times a polynomial can be given in factor form. So why am I using such an abstract word many times? Like how many times is it like 90% of times or 100% of times, or only a few times out of 100 times? Just think as closely, in order to answer that abstract question right there, just think as closely as how we were working with quadratic, for example. Not all quadratics have a factor form. Okay? If you recall from our previous learning experience when we were working with quadratics right there, it's not always easy. The number one thing is it's not always easy to find the factor form of a quadratic, and that's number one thing, okay? And that's why it's already reduced down the amount of times we have a polynomial given as a factor form. And precisely speaking, there are also quadratic where we cannot factor out. There are also quadratics that we cannot factor out. That's why, like I said earlier, not all quadratics have a factor form. Okay, so just like that. Now with that generality, we carry that generality into just any general, high degree polynomial. Yes, many times. All right, that's all I can say. Many times, any polynomial can be given in a factor form. And so don't get me wrong on this. I am not going to give a lesson about how to factor, because when the degrees start going beyond degree 2, okay, when degree goes higher than degree 2 or power 2, then higher than a quadratic generally, then it's getting really extremely hard to look for a factor form. So that's why all I'm saying is many times we have a polynomial given as already in factor form. That's all I'm saying. Okay, usually we're not expected at our class here when we're dealing with polynomials being higher degree than degree 2, then we're no longer expected to find a factor form of that. But rather than that, we're given a polynomial in factor form. Okay, and that's why I'm saying many times a polynomial can be given in factor form, and then we are expected to know how to work with that polynomial in factor form. All right, so now allow me to show a demonstration problem, and it's still not a formal example. Because, and the reason I formally bring this into our lesson here, because, surprisingly, quite a few textbooks out there skip this details, but do give exercises and problems along this way right here, but without much explanations about it. So I really want to give some insight, the explanations before any one of my students who, after viewing this lesson, can be able to do your own exercises and problems out there. Okay, so just think about it, something like this. F of x equals, all right, so we can have an x minus 1 times x plus 3 times an x minus 2. All right. This is what I meant by, and now it's a polynomial. Okay, it's a polynomial, and it's given in factor form. Okay, and now one more thing. Each one of these, ideally, each one of these factors, so it's a factor right here. These are all factors. So now ideally, these are the factors are linear, okay, or linear expressions. Okay, ideally the factors are linear expressions. Okay, but then and for simplicity of this course, I don't want you to worry about the other cases where the factors are not linear expressions. I mean, there are cases where the factors involved some irreducible quadratic. Okay, but if we have to get there, I'll mention it. Otherwise, most of the time we stay with those of, these are the given polynomials, and they are in factor form where each factor is itself a linear expression. You see, this is a 1x minus 1, this is a 1x plus 3, and this is a 1x minus 2. That's what I meant by linear. So each of these is itself a polynomial, a literal polynomial, a linear polynomial, degree 1 polynomial. Okay, so ideally, when you're working with a polynomial like that, right, then these should be a lot of times all linear expressions or linear polynomials, literal linear polynomials. Okay, so that's just to mention about the kinds of function here. So it's in factor form, and it's completely legal to be a polynomial here. But now, what do we do with something like this? So when I first introduced about the polynomial, then we talked about the leading coefficient, the leading terms, the degree of a polynomial. But see, we were able to identify all of that information. For example, if we're looking at f of x equals minus 5x to the 7 plus 3x to the 4th, for example, and then just stop at this little short example with two terms. But see, we see clearly that this is the leading term where it tells us about the degree of our entire polynomial here. So this is degree 7. But see, we identify that information so easily simply because all terms are written out. And this polynomial is not in factor form. This is in general form. All right. So now the challenge is here. When we have something like this. All right. So when we have something like this, then, and sadly somebody is asking us, identify the degree of this polynomial. Okay, what degree of the polynomial is this? All right. And so for this one time, allow me to do the following. Think about the foiling. Just think about the foiling. Okay, so x minus 1 times x plus 3. So foiling gives me, and I'm still not doing anything with the x minus 2 yet. Okay, so x minus 1 times x plus 3. So foiling it out, it gives me x squared. Okay, and so this is simple enough that you can also take your foiling work independently alongside with watching this lesson right here. And then now it's going to give me a plus 2x but minus 3. Okay, so just simply multiplying out. So now we already ran into a degree 2 polynomial here, being in product with this degree 1 polynomial. But we have not completely foiled out things yet. So I'm going to take one more step, foiling. So x distribute for each term here. Okay, and then that minus 2 is distributed for each of these terms right here. Okay, so now I'm looking at, see, so the x times the x squared here gives me an x cubed. Okay, and then here plus 2x squared minus 3x. Okay, and then that minus 2, so minus 2x squared minus 4x and plus 6. And then we're going to combine like terms. Okay, so these are the like terms, but they are also the opposite terms. They got canceled out. Okay, and then these two are combined together. All right. And that now gives me the final simplified version, the final version of this expanded polynomial, or in general form. It's a x cubed minus 7x plus 6. And so now once we have put our polynomial in expanded general form like this, then now it's easy to find the degree of this polynomial. It's degree 3. Okay, it's degree 3 polynomial. Okay, and then leading coefficient is 1. Okay, we've learned all of that term right here. Okay, the leading coefficient equals 1. Okay, because that coefficient here. But so the question now is, really, do we have to FOIL out every single time just to find the degree and the leading coefficient when we are sadly given a polynomial but in factor form? Do we have to do this foiling work every single time we're given a polynomial in factor form and asked to find the degree and the leading coefficient? All right, so the good news here is, nope, we don't have to. So let me point that out right here. We can completely bypass all of this foiling work. Just think about the following. Okay, so anytime you are given, so it's now just experience, really. I don't want to make it too formal of a lesson, but anytime we're given a polynomial that's already written as a factor form, that's already given in factor form like this. Okay, see, just think about, you simply need to multiply the x here, the x there, and the x there. And this factor itself appears only one time. This factor itself has power 1, and I mean appears one time means power 1, power 1, power 1. So just that, x times x times x. It has to give me equivalent to x cubed. And that's already enough to say that our polynomial here, if we FOIL it out, it's going to be a degree 3. Okay, we just simply think about that's why, like I said, ideally we look for linear term, because each of these is a power 1. Okay, each of these is a power 1, and then so the power 1 here plus with a power 1 plus with a power 1, the total of these individual powers is a degree 3. Okay, so power 1 plus another power 1, that gives me a total degree being degree 3. Okay, and then the leading coefficient. So ideally in the easy case like this, where all of these are power 1, and then each one of these has just the coefficient 1 on each of these, a linear expression, then it's just think about 1 times 1 times 1. It's going to be lead coefficient equals positive 1. All right. And then so I will bring up more experience along that way in the following example. So now I only just need to put into your awareness that there are times, and quite often, okay, there are times your polynomial is given as in factor form. Okay, in factor form. So in order to decide the degree and the polynomial and the leading coefficient, we just need to add up or sum up all the powers in each of your linear x term right there. Okay, so here, for example, as a quick example, it's power 1, power 1, power 1, summing up all the 3 individual powers. It's a power 3 finally. And so our overall degree should be a degree 3 without multiplying through. All right. And so now, so at this point, let me introduce another demonstration right here. So there could be even times where, and this is what I really want to get clear before we can get into some formal example to apply our understanding. So as I said earlier, there could be time that we are given polynomial in factor form, but sadly, how about something like this? All right, and then all right, so it's in factor form, but one of the factor here appears to be not linear, but then irreducible, meaning we cannot put this in factor form any further. Okay, so this is pretty much at dead end. But so in the end, what is the overall degree for something like this? See, power 1 here, so this is a good ideal case right here. We got the linear expression, but here it's a quadratic expression. But no worries, let's treat things the way similar to how it was in the earlier little problem I brought up. So it's power 2 here, the degree 2 for this factor, degree 2 for this factor, degree 1 for this factor. So now I'm using that proper term right here to make things really clear. Degree 1 for this factor, degree 2 for this factor. Okay, so now the overall degree for this entire polynomial, okay, it's simply just degree 1 total up with degree 2 right there. That gives me a degree 3 totally. All right. And then yes, leading coefficient for something like this. Again, simple. Okay. I see a coefficient 1 with that polynomial, another coefficient 1 with this polynomial. So coefficient 1 times coefficient 1, the overall leading coefficient. Well, I accidentally skipped out the word leading, but I meant to only focus on the leading coefficient. So multiplying all of these leading coefficients, we're looking at just a positive 1. So this overall right here, without the need to FOIL out, we can still predict quickly. We can still expect precisely, indeed, the overall degree is a degree 3, and then the lead coefficient would finally come out being positive 1 in this case. All right. And then another case arises right there. There are times where you are given a factor form, a polynomial in factor form, and then some factor has a power as following. Say this is a 2 plus 5, and then x plus 5 and x minus 1, and unfortunately the x plus 5 here is raised to the third power. Okay, so we will get to this term formally, but on this particular factor, this means x plus 5, this power 3 here means x plus 5 times x plus 5 times x plus 5, okay? That's just a quick explanation about that. That's what the 3 here means. We think of that as 3 identical factors x plus 5, and then multiply with x minus 1. So now measuring the final degree, the overall degree of this polynomial, now it's becoming clear. Degree 1, degree 1, degree 1, degree 1. That's making a total of a 4th degree. So the degree here, this overall polynomial, okay, this beginning one right there is degree 1. Degree 4. All right. And then lead coefficients again. Right from here, you can see coefficient 1, coefficient 1, coefficient 1, and coefficient 1. Okay, so lead coefficient finally would come out to be 1, because 1 times 1 times 1 times 1. Okay, and then as you build enough experience, you're gonna see that, hey, with something like this, you don't even have to write it out as 3 identical factors. You can just count directly from here. This is degree 1, but then it's 3 times. That's what this is. And so for that reason, okay, so let me do a little sidetrack right here. But so sooner or later, you're going to learn this number right here is called, for now, I call it, it's a multiplicity. Multiplicity. Okay, multiplicity of that factor x plus 5. So it's right now I treat that 3 here as a multiplicity for this particular factor. And then later on we will learn that term multiplicity even more formally. Okay, so since this factor here has multiplicity 3, that means whatever degrees we recognize for the polynomial inside of that, this is degree 1, but we have to triple that. That's why it's, so now total here it's degree 3, and additionally add with that degree 1 here, it gives us a total degree power 4 right there. All right, and so now let me bring in a different, slightly small situation. And we can have a polynomial that is, so it's still a linear expression, but it's not as simple as the earlier cases we've seen. Like say here it's a 2x minus 1, and here it's a 3x plus 5, okay, and here how about a 4x plus 3, something like that, okay. And now how about I'll put a multiplicity here. Okay, so with something like that, now finding the degree is simple. Degree 1, sum up with another degree 1, so that makes degree 2. This is degree 1, but multiplicity 2, so that's degree 2 together here. So all together it has to be degree 4. Okay, that's now easy to determine. Okay, but what about the lead coefficient this time? All right. So just think about if you would have to FOIL out, then as part of the process, this leading coefficient inside of this small factor right here has to eventually multiply with 3. So 2 times 3. But then we need to also multiply with 2 times of that 4 right there, because it's a leading coefficient 4 in this factor here, but it's raised to a multiplicity 2. So the multiplicity does impact your leading coefficient work as well. Okay, and so now that's going to be your overall lead coefficients, and signs count too. Okay, so now that makes it 6, and times it 16 altogether. Okay, and so that's now making it 96. All right, that's now making it 96. Okay. And so now at this point right here, one last case right here, okay, then we can, in factor form, okay, in factor form, we can also, a lot of times your polynomial in factor form comes with a coefficient in front already. So let's say we have a 1/5 here, and then there's a 2x minus 1, okay, and then there's a 5x plus 3, but square, for example. Okay, and then, so with something like this, in our experience up to this point, yes, this overall polynomial has degree, okay, degree 1 for this linear expression, okay, degree 1 here, but 2 times, so it's going to be plus 2. All right, so it's the total degree here is 3. But now what does, now, so what about the lead coefficient? All right, with the lead coefficient in this case, see, so very similar to that demonstration problem I've done earlier. So this is 2, okay, I'm going to multiply with 5, but not only one factor of 5, it's 2 factor of 5s, okay, 2 factors of 5 right there. And then I also need to multiply with that 1/5 as well. Okay, so we multiply all of these coefficients together to come up with our overall leading coefficients. All right, so now it's going to be canceling out as a quick math right there. And so here we're looking at the coefficient, leading coefficient 10 for that. All right, so all of that details now, I feel that I have ensured you have seen enough different cases for how a polynomial can be delivered. Okay, so now let's drive it into a certain example over here. So I'm going to call that the next example, where I'm going to be able to just apply our skill. I'll show you the steps by step, and this is still among one of those examples where it goes directly out from what we learned here. Okay, so it's not an apply example. Okay. All right, so now this example 3 here is simply one class of problem where we just simply practice. Okay, so now we just simply need to determine the degree, okay, because that's a very common word. And once we get fluent with the skill right here, then in one day you're just simply given a polynomial and you will know within seconds the degree and the leading coefficient. And this information is so important, sort of like the leading information, okay, for any polynomial. The first thing in line we need to identify for any polynomial. So determine the degree, okay, and the leading coefficient, okay, of the following polynomial. All right, so let's now call that part A. So I'm going to start mixing between, a few of these problems, a few of these polynomials, or in general form, and some other ones given here in factor form. Okay, so what about f of x equals minus 7x to the 4th minus 2x squared plus 3. All right, so something like this. Simple, because it's already in general form. Focus right in that leading term right here, the term that has the highest degree, that has the highest power, okay? All right, so now clearly this one here has degree. This one here has degree 4. That's simply the highest term, the highest power recognized throughout all the terms. We have a constant term, we have some other terms, okay? Power 3, it's 0 coefficient. Let's not worry about that. Power 1, not written here, 0 coefficient. Okay, but now this is the determination for the degree right here. Power 4, the highest one ever recognized. Okay, so that's why degree is 4. Lead coefficient or leading coefficient must be -7, whichever the coefficient in front of your leading term. So leading term is here. Focus right on that. All right. So let's look at another one. So I'm going to leave some part of the work solution here, so that because I don't want to keep rewriting it. Okay. So degree and lead coefficient, because that's what we're looking for. Let's look at now part B. All right. So in part B right here. How about, let's look at g of x. I'm getting really tired. I keep using f of x and f of x the whole time through like that. So we can name our function differently, even though it's a polynomial still. So how about negative 0.001 x squared plus 0.03x minus 5 here. Okay, it's a polynomial in general form. I purposely put anyone viewing the lesson here in that case where your coefficients appear to be nasty decimals like this. Okay, but we just pay attention to the general form. It's a polynomial. In general form, it's arranged in the way of power 2 and power 1 and power 0. As a matter of fact, for anyone after this course is going into a business field, you will learn a lot about the kind of math where you see these kind of coefficients a lot in your polynomial there. Okay, so now the degree for this polynomial is degree 2. The lead coefficient, admittedly quite nasty looking, but it's negative 0.001. All right, negative 0.001. So that's how we found our degree and the lead coefficient. All right, so I have introduced among my demonstration problems quite a few and good enough details. So now in this example, allow me to put in a problem where we're going to need to apply things a little more creatively. Okay, so how about h of x here is going to be, how about negative 1/2, okay, there's x cubed, okay, times in factor over here 2x plus 1 times, and how about minus 3x minus 1 squared. All right, so now we are given a polynomial in factor form right there, in factor form. See, I did not ask anyone, and as a matter of fact, when we arrive at this level over here and specifically focus on learning about polynomial, that we won't have to be too bothered with how to factor out polynomial, but rather than we know how to handle a polynomial that's already in factor form. Okay, so now degree. Let's identify the degree. The degree of this polynomial as well as the lead coefficient. All right, so the degree here. Don't look down on that simple factor but dangerous. This really means, see, this is the little detail that I was not able to mention, that I did not mention when I was bringing up the demo problem, but is this still a linear factor? Yes, it is. I see this as, just make a good note for this. I see this x here as x minus 0. It's still a linear factor, and then raised to a third power. All right, and then here is a easy to recognize linear factor, and then a linear factor here, but raised to a multiplicity 2. And by the way, this x minus 0 as a linear factor raised to multiplicity 3. All right, and so now we are ready for identifying the degree right here. So the degree, this x right here, linear, degree 1, has multiplicity 3, so it's going to have to be 3. Okay, and then that's just a coefficient. Now this is degree 1 and only multiplicity 1, so I'm going to add one more additionally. Okay, and then this x right here is degree 1, but then with multiplicity 2 overall, so we're going to add another 2 right here. So the overall degree here has to be, so that's going to make it 6. So our polynomial, if we would FOIL it out, it's going to be an overall degree 6. All right, and then what about the lead coefficient? Very similar to the work I've done. Okay, so the very front coefficient, I wouldn't say that it's the final lead coefficient yet, okay? Just because it's standing really in front doesn't mean it has to be the only lead coefficient. All I see is, formally speaking, a negative 1/2 is there. This x cubed right here, the coefficient for that x term here is a coefficient 1, but to the third power. So now it's multiplied with 1 cubed, okay? And then we multiply with a 2 here, because it's to the power of 1. Okay, so that's only need to multiply one time. Now be careful with that. So it's negative. It's negative 3, but I have to raise it to the second power. All right, so all together is negative 1/2 times 1 times 2. Now negative 3 all square is a positive 9. So all together my overall lead coefficient, if we would FOIL out this thing, will become a negative 9. All right. That's the final answer for this as the leading coefficient for this overall polynomial. All right. And now I can generate another one. All right. So in part D right here, let's look at how about a p of x, a perfect name for a polynomial. That's what p is for. Okay. So how about a 1 over 16, okay, times 2x minus 1, okay, and then times 4x squared plus 1, okay, and then multiply with a negative 5x plus 1 all squared. All right, so something like that. In factor form again, where degree and lead coefficient information are not so trivial, and we have to do some work around to find that. Whereas versus the general form, and it's just right there, we see it immediately. All right, so now let's look at the degree. All right, so this is what I found right here. This is degree 1 for x, and only raised to multiplicity 1. So it's 1. I'm going to add with, now this here is an irreducible quadratic factor, meaning we cannot factor this any further. So look at this x right here, it's already a second degree. So that degree right here I'm going to add with 1. So 1 for this, 2 for that x squared, okay, and then I'm going to add with, so now it's admittedly it's a linear factor, but has multiplicity 2, so it's power 1, but it's multiplied 2 times. That's what multiplicity, another way of explaining about multiplicity. So that's now I can legally add 2 to that. So 1 plus 2, our final degree is a degree 5 for this overall polynomial. Okay, and then when it comes to the lead coefficient, okay, we also have to do the math a little carefully here. So just because this 1 over 16 stands in front doesn't mean it's going to be the final lead coefficient, but it's still being part of that. So 1 over 16, I'm going to multiply with, so now the lead coefficient in this particular factor is a 4. We're going to multiply that with that, okay. And the lead coefficient, somehow I skipped this, but now I'm going to get back to that. The lead coefficient for that factor here is a 2, so let's multiply it in, okay. And then the final one here is having lead coefficient being negative 5, but then it has a square, a multiplicity 2. So really it's a minus 5, but all square. All right, and now let's multiply all of those factors together. So in the end here, it gives me an overall lead coefficient. Now the negative 5 after squaring is going to give it a positive 25. The 4 times 2 cancel with the 16 right there, giving me a 1/2. So in the end is a positive 25 over 2. That should be our final leading coefficient for this polynomial, which was given in factor form. All right.